Thank you for the introduction, and great to be back at MIT. And excited to talk to you all about my research and kind of my vision for where I think a lot of cool research can be done in AI for Earth very broadly. Yeah, I'm a senior applied research scientist at Microsoft Research. I did my postdoc here at Microsoft Research New England, and now I'm technically at the Redmond team, just haven't moved yet. So it was a very short commute for me. I want to start my talk by this little, oh, it even has the sound, nice. By this little time lapse. So what you see here is a time lapse of objects in lower Earth orbit since the 1960s up until all the way to today. And what you can see is this kind of steady growth of more and more objects over the last 6 decades. Now, many of these objects you see here are Earth observation satellites, so satellites that sense some aspect of our planet. And the question for me since a long time has been, with all of this sense data of our planet, what can we do with it? And what do these satellites observe? And yeah, we're about 10 years off from today, a bit more, but you see it's getting really cluttered up there. And I don't know if you've noticed, but sometimes you look up, you can, for example, see the Starlink satellites in these like little neat lines traveling through the sky. So it's looking very different to even when I was a child. Now, as I said, there's more and more satellites being launched almost every day. What you see here is just kind of the expansion of the ESA mission, so the European Space Agency, up until the 2030s. Obviously, these satellites produce a massive, absolutely massive amounts of data. And I think to kind of put that a bit into perspective, if you think about the latest generation large language model, something like GPT-4, we don't exactly know how big the training set for those models were, but it's hypothesized or estimated there was around 1 petabyte of tokens worth training data. And keep in mind that for this data to be generated, OpenAI basically scraped every single existing text that exists. And some people, think also they kind of translated YouTube videos and made that into text. So we don't know exactly, right? To compare Earth observation data with that, the kind of current estimate of all of the Earth observation data out there is 800 petabytes, with another 100 petabytes being generated every year. So we're kind of working on completely different orders of magnitude here. And it isn't really just satellites. A large portions of all of the world's data have geographic metadata attached to them, right? So beyond the satellites, we might have something like a geotag tweet, so social media post that has been sent from a specific location. And then we have also like derived products like elevation or species range maps at a given location. Now, I really believe that there's lots of potential in combining these geospatial data sources from different ground and remote sensors together to support decision making. And for this, we can leverage their joint geography, their joint geometry, being able to map them on the sphere of our planet. And I'll show you a little example of what I mean with that. For example, we could combine this geotag tweet, which is from Annapolis. It's about a flooding event. Oh no, that was too fast. I wanted to do this, right? So this is a tweet about a flooding event in Annapolis. We can combine that with real-time meteorological data that comes from a satellite, for example, to make some informed decision. For example, should an evacuation order be issued or not? So this seems very intuitive, right? This combination and the support of decision making. So why isn't this being operationalized at large scale? And I'm breaking this down very, very roughly, but I think there's kind of 3 overarching problems that currently exist. The first one I got to already is the sheer scale of this data. The second one is that this data is very unstructured and multimodal, right? So we're working with images, video, very, very different data modalities. Unstructured is that they're like in different archives, different from different providers. Some of them are behind paywalls, some of them you have public access to. And the latest big problem is that a lot of this data is unlabeled, right? So while we have satellite imagery for the whole world, we only have kind of limited labels that tell us what exactly is in this satellite image at this location at this point in time. And with my research, I'm kind of trying to tackle all of these problems at once. Really ambitious, but I think there's some interesting solutions here. For the large-scale problem, very kind of, in vogue solution is to use neural networks, kind of the best scaling method that we have to deal with large amounts of data. To tackle the kind of unstructured multimodal nature, like I said, I believe we can fuse different modalities, different information of our planet together in their joint locations in space and time. And then lastly, to tackle this problem of the largely unlabeled data, I think we can leverage advances in self-supervised learning, so learning without labels. And the type of models I want to talk about today and that I believe have the potential to fulfill all of these parameters are geographic location encoders. And these are highly scalable neural network models that use self-supervision to learn semantically meaningful representations of our planet from these large amounts of Earth observation data. And throughout this talk, I'll kind of show how we built the first generation of these models and then where we go from there. And the way I want to structure this is first I want to talk a bit about the origins of the spatial modeling problem. Then I'll outline location encoders and how they currently look. In part 3, I will talk about how to train them with self-supervision. And in part 4, I will talk about the kind of looking ahead, what is up next. All right, so let's start with learning from geographic data. So the classic description of the geographic modeling problem is that for a given location, lat and long, we want some output. And what we can leverage here is the first law of geography. All things are related, but near things are more related. For example, for a good temperature estimate at our current location, the best thing we can do is we can look up the closest available temperature sensor and then weigh our estimate somewhat on the distance between us and that sensor. And so we can get from a few sparse observations, we can kind of build a dense map that exploits this spatial smoothness. Classic interpolation problem. Traditionally in geostatistics, we would use a Gaussian process for this. In geography, it's also often called kriging. So we would basically learn a continuous function over space using kernels. One problem with these kind of traditional methods is that they scale pretty poorly, right? So Gaussian processes and kernel methods have cubic complexity, and while there is some work on, for example, deep Gaussian processes that help that a little bit, we kind of still struggle with the pure scale of that data. Gaussian processes are also not the best models to work with kind of very complex data types like images or so. And lastly, at least vanilla Gaussian processes are also not able to deal with the kind of spherical nature of latitude, longitude coordinates. You can use something like a spherical kernel, but again, there's some shortcomings. So we are machine learning people, right? So why don't we just replace the Gaussian process with a neural network and solve all of these problems? Unfortunately, that's not so simple either, because neural networks also have some problems. Sure, they scale better, but they also, for example, don't necessarily work on spherical coordinates and can deal with the kind of non-Euclidean nature of geographic coordinates. So what we do here is then we want to kind of build the best of both worlds, neural network architecture that is able to deal with the spherical nature of the coordinates, and that is the geographic location encoder. And the idea here is to first embed our location coordinates, or latitude, longitude, using some positional encoding. This is, if you're familiar with transformer architectures, it's basically very similar to how transformers do positional encodings. And then we put a neural network on top that learns a weighted function of these positional encodings to solve our task at hand. And hopefully this can then scale to really high-dimensional data. And again, we kind of do the same thing we would do in a GP and learn this continuous function over space. The other thing we can do with this is that location encoders also give us the flexibility to integrate them with other neural network models specialized for different inputs. For example, images. And this is the idea that behind geographic priors. So for example, here we have an image classification task where we want to classify the image of this fox. This is an Arctic fox. If you think about this task kind of location agnostically, it might be a bit difficult to exactly place these animals. Foxes are all around the world. But knowing the location of the fox will allow a model to learn internally some sort of species distribution model, and will have the model learn that you can only find the species in certain latitudes. And so geographic priors are relevant for many different applications, not just kind of species classification, but for example, also for building segmentation or soil carbon estimation. All right, so done with part one, the kind of description of the spatial modeling problem. Let's go into part two, the location encoding basics, and this is mostly based on our ICLR 24 Spotlight paper, which you can all check out. So here I briefly describe how location encoders should be designed, how they were designed in the past, and what the current state of the art is. All right, so let's start with a few formalities about location encoders. I'm not going to go into all too much detail, but basically this is kind of the very simple form they take. You have your locations, C, so these are latitude, longitude coordinate pairs, that are fed through a positional encoding. This is purely a functional transform, right? So there's no learnable parameters there. And then the output from this positional encoding is going to be fed into a neural network which has learnable parameters, and that is our location encoder. Quite simple, but of course we can do a few different modifications here. And the first one I want to talk about is the history of the different positional encodings that were used. The kind of first positional encoding we can look at in the machine learning literature is from a 2015 CVPR paper that does very, very simple one-hot encoding of the coordinates. So the idea here is that you split your whole world into grid cells. Each of the grid cells is one value in your tensor, let's say, and all of them are 0 values except the one grid cell that your location falls in, that's a 1. So very simple, similar to other one-hot encoding methods in other areas. Obviously not the most sophisticated positional encoding, and so in 2019, also at CVPR, we saw kind of the first bit more sophisticated version of positional encodings, and that was the first sinusoidal one. Same paper as the paper I talked about before with geographic priors and image classification of animal images. And so here the idea is to use sine, cosine activations, very much again the same intuition as for transformers. And so here you project your latitude, longitude coordinates from 2-dimensional space into 4-dimensional space, doing cosine lat, cosine long, and sine lat, sine long. And over the recent years, the kind of state of the art has been to make more sophisticated versions of this. For example, the multi-scale sinusoidal encoding, where you basically do the same sine cosine functions, but you do it at different frequencies, basically by dividing the values by this alpha here, which is your scaling factor, and you can do that at arbitrary intervals to get more and more fine-grained embeddings. All right, so this is kind of the work up until maybe 24, but there has not really been a fundamental shift in the way these positional encodings were done in this kind of sine cosine formation, and the work that we're doing is changing this, and I'll get to that in a second. The other part of the position of the location encoder has remained vastly unchanged over the last years, and that is the neural network component. So basically, what people have been used here is simple fully connected layers, so simple MLPs. This is also something we're going to change in our paper. And the reason why we adapt this a little bit is that existing location encoders up until us had two major shortcomings. First, performance of these location encoders falls off drastically around the poles. And the reason for that is that these location encoders use sine cosine positional encodings that assume Euclidean space, and around the poles, this diverges the most from the true spherical space of a planet, and so we should probably replace them. The other problem is that simple, fully connected networks are not necessarily equipped to learn these kind of smooth spatial functions that we want, smooth functions over space that we want. And so we want to tackle both of these problems at once in our work. And the solution for the kind of first problem in the positional encoding is that we're using spherical harmonics functions instead of simple sine cosine activations. And the answer for the second problem is that we don't just use fully connected networks, but we use sinusoidal representation networks, so sine activation functions. Yeah, let me get a little bit into the first component, the spherical harmonics positional encoding. So spherical harmonics are widely used in geodesics, fluid dynamics to model our planet. So this is kind of the status quo in geophysics. And I'm not going to go much into the math here, but basically spherical harmonics are orthogonal basis functions that are natively defined on the sphere. And they come in different numbers of degrees, L and orders M. This is kind of the full function here, but I guess in the interest of time, I'm also not going to go too much into this. And while there is a closed form solution for the spherical harmonics, we can also analytically pre-compute them, which is really nice later on in our neural network training, because that makes everything much faster. Now, there is a really cool theorem that says that any function on the sphere can be approximated by a weighted sum of spherical harmonics functions. And so the question now becomes, how do we get these weights for the weighted spherical harmonics functions? And our answer is that we use a neural network to get these weights. So we use a neural network on top of our spherical harmonics positional encodings to, hopefully approximate any function on a sphere. And to better learn smooth spatial patterns, we use a neural network architecture that comes out of vision, especially 3D vision, and that is the sinusoidal representation network that was actually proposed by Vincent Sitzman, who is right here at MIT. And yeah, they've been shown to be extremely effective at learning neural implicit representation, which are, again, these functions that are continuous in space. And you can think about this from a kind of 3D vision perspective as a point cloud problem. We have point clouds in 3D space, and you want to build some continuous mesh or map out of them. And basically, we have the exactly same problem on the sphere of our planet. And the trick with sinusoidal representation networks is really simple. And it's just changing the activation function in a neural network to a sine activation function. That leads to some computational issues if you stack a lot of these layers, because computation gets more important, gets more expensive, but we're not really dealing with large neural networks here. All right, and then again, we hopefully can learn these kind of weighted spherical harmonics to solve functions on the sphere. Let's put things together. We can use location encoders just like we would use Gaussian processes or other interpolation methods and learn from kind of sparse observation a continuous map in spherical space. For example, we can use them to learn a map of landmass globally. Right, so here we sample, let's say, 5,000 locations on the planet. We give them each a 0 value if it's water, not landmass, or 1 if it's landmass. And then using our spherical harmonics location encoder, we build like a dense map. And you see, depending on how you set your scale, this works quite well. Let's look at the two components of our new location encoder separately. So first, Siren neural nets are better than existing linear or fully connected backbones for learning spatial patterns, which you can see here, right? So on the top, we have kind of the exact same positional encoder backbone, our spherical harmonics, but on the top, you see a linear neural network, and on the bottom, you see a Siren neural network. The L5 hyperparameter here, that's basically the number of Legendre polynomials we use in our spherical harmonics. So the higher, the more fine-grained our spatial resolution is, which you can also see. And you see that the Sine neural network just gets much better resolution. Now, let's look at the other component, the spherical harmonics positional encoding. And here we want to specifically focus on the poles areas. Remember that I said that existing methods often fall short on the poles because the assumed Euclidean space of kind of Fourier transforms diverges the most from the actual spherical space. Let's look again at our Arctic fox. So here we do Arctic fox image classification, and you can see that a model that uses one of the existing positional encodings that is not spherical harmonics based has much more artifacts that are completely far from the poles compared to our method. Another example here, this is a different, this is synthetic task, Fibonacci checkerboard prediction. Here you can see in the figure, the red line is our spherical harmonics method, and you see that it remains quite accurate around the poles, whereas other sine cosine based methods fall a bit off here. All right, so that's it for part 2. To recap, so far we've discussed how to design state-of-the-art location encoders and how to train them directly, right? So here the input was lat long and the output was some value, right? Landmass, yes, no, or some climate variable, right? So we have like a direct classification or prediction problem. The next part of the talk will focus on pre-training location encoders with unlabeled Earth observation data and how this can help us improve modeling downstream. And this, I should have updated that slide. So this work is based on our paper SACCLIP, which is not under submission anymore, but a AAAI paper next week in Philadelphia, if you're around. And why do we need this step? So far, we've basically only talked about spatial interpolation. But a big question in geospatial modeling is, of course, also, can we do extrapolation? And spatial extrapolation describes the problem when we want to make a prediction geographically far from our training set. And we cannot rely on the first law of geography, or just kind of looking at nearby observations, because we just don't have any nearby observations. And I believe that using this globally available Earth observation data and our location encoder models, that we can actually make a big step towards kind of more general approaches for geographic extrapolation, which is one of the kind of big long-standing problems in geospatial modeling. And to kind of outline the intuition for that a little bit, I want you to think about the Earth as a bounded space, right? It's a completely bounded space. We can kind of capture all of the planet with satellites. And sure, some areas might have more or less cloud coverage, but in the end, we can kind of observe everything. Plus, there are sensors that see through clouds like radar. And now, if we assume that Earth observation data is roughly relevant to a lot of tasks, we can hopefully leverage this kind of data to capture ground conditions that are relevant to our tasks and infuse them in our location encoders and have them available for the whole world. But the question is, how do we go about this pre-training? All right, so again, the intuition is location encoders fail when deployed in unseen areas. Question is, can we pre-train them on globally available Earth observation data so no area remains unseen? And to revisit our kind of Arctic fox prediction task, instead of doing this conditioning on the geographic location like from scratch, basically just feeding in the coordinates, can we, instead of just the coordinates, feed in some semantically meaningful vector embedding that represents this location? And to get to this embedding, and to explain the intuition for how this pre-training works, I have a little game that we can play, and the game is called Where is this satellite image? So hopefully you can, basically GeoGuessr, but GeoGuessr is like with street view imagery. Now you have the satellite view, right? So anyone have any idea where this image is? Sahara? Okay, any other guesses? We have Sahara. So that's Northern Africa. Eastern what? Eastern Africa. Okay. Any other guesses?
Boston Harbor.
Boston Harbor. Okay. I think so. I actually need to see because I don't think you can see it so well.
Scale? Like, what is this?
Yeah. So this is 2.5 by 2.5 kilometers. I think it's a bit hard with the beamer view. This is always a bit the tricky bit of the talk because it kind of always depends. Like at least the screen is very big. Okay, so everyone's guess was very wrong. This is a picture in the Arctic, somewhere in Canada. And so this, now we know where this picture is. What I want you to do next is I want you to think about, if you now know this location, think about what characteristics in this image might make you think of that location. And again, so I happen to know where this is. And so I can walk you a little bit through what I think are kind of relevant characteristics. So in the top here, we have this little white patch. I don't know if you can see it well, which could be snow. Then we have this rugged kind of maybe glacial moraine. And then down here, and this is the bit you can't really see because of the contrast, but there's a coastline here, right? So there's some water here. And all in all, these three features might give you some indication that this is kind of in the Arctic Circle. And the true location can actually be predicted quite well with a neural network. And this is exactly how we're going to pre-train our location encoder. And the way we do this is very much similar to CLIP. CLIP is a model by OpenAI that matches text and image pairs. Only in our model, we match image and location pairs, right? So we take a bunch of globally distributed Sentinel-2 images with their corresponding locations, and then we have a contrastive learning objective where we feed our images through an image encoder, locations through a location encoder, and then we match the correct images with the correct locations in a batch. And the idea is then that if this training succeeds, we can take forward this location encoder and obtain semantically meaningful embeddings for every single location on the planet. And if we train this on enough data, this model should learn to interpolate and even work for unseen locations because it will interpolate from the nearest seen observations, leveraging the first law of geography, and learn this kind of smooth embedding map, so to say. And yeah, so the way this works is that you have like a bunch of different image embeddings you get, of course, and you have a bunch of different location embeddings you get. But throughout this matching process, you learn to align them and to transfer the features that make an image look unique to a location into the location encoder. And so now downstream, you don't need images at all anymore because you assume that the most important image features are now part of the weights of your location encoder. And you just have a model that takes in latitude, longitude, and returns these embeddings. The embeddings in our case are 256 characters long. So they're not really able to capture super granular structure, like how many cars are in this picture or so. They only capture very high level features. And one of the high level features that they capture that we can show is biomes, right? So here you have a dense biomap of the whole world. And now again, think of an interpolation task, right? So you take 5,000 random locations and try to build this map from scratch again. From these 5,000 locations, sparse locations, build a dense map. If you do this just using the location encoder trained from scratch, no pre-training with our SACLIP method, you get to this map. So you get not a very good accurate map of biomes. Now, if you do this using our pre-trained location encoder instead, you get to a very accurate biomap. So we basically see through this that our SACLIP embeddings, capture at least to some degree the conditions that make out a biome. Now, this is an interpolation problem, and when I started this section of the talk, I said that SACLIP can be really useful for extrapolation, right? So what am I doing with interpolation? And to explain that a little bit, we play a second round of the game. And the second round of the game has now this image, and again, question is, where is this? Can I again have some thoughts? Yeah, same size, 2.5 by 2.5 kilometers. Any thoughts? Australia, okay. South Africa, nice. Okay, so I assume you see some, it's like reddish, you think it's in the desert? Okay. Turns out it's not at all in South Africa or in Australia. But it is a desert, right? It's in Arizona. Now, obviously SACLIP will get that right? Because, it's a big AI model, it knows everything. Turns out SACLIP also gets that completely wrong, right? It thinks also that it is a desert, but just like you, it just thinks it's a different desert. And it turns out that a lot of places around the world actually look very similar. And if you just look at satellite imagery alone, there's no features that actually make it distinguishable. Now, you might think that this is a failure mode of the model, but it's actually not at all the case, because SACLIP predicts a different location because both locations, again, have the same features. And what this can tell us is which areas around the world are visually similar. And this insight we can then leverage to train models for one area where we don't have labels on another area of the world where we have labels that is visually very similar. That is the idea. And to kind of hone down on that intuition a little bit, here's a similarity map of SACLIP embeddings with different anchor locations around the world. Right? So on the left side, we have a location in the Congo Basin. We take that location and compare it to every single other location on the planet and see how similar is that location. And obviously, the most similar locations are going to be other locations in the Congo Basin, super high similarity score. The redder, the more similar. But we also see that very geographically distant locations, like in the Amazon or in Indonesia, also have high similarity scores, even though they're very geographically far. Same with on the right side, a map of the US East Coast. Again, the most similar locations are also in the northeastern US, but there's also a lot of similar locations in Europe or in in East Asia, like China, Japan, kind of very built-in areas. And again, the intuition is we might want to train a model for the Congo Basin, but we don't have any training data available there. But we might have training data available in the Amazon or in Indonesia. So if we train our model on that sort of data, it should transfer quite well to that new unseen area. And we can test that intuition to some degree by doing geographic domain adaptation experiments. So here we basically hold out a whole continent as a test set and only train on all other continents as training set. This is a few shot setting, so we actually give it very limited number. I think it's about 100 of points in the test continent, just because in this example, we try to predict ecoregions, and ecoregions can be unique to a continent. And SACLIP gets that much better than some existing location encoder models. There is some that exist already. For example, GeoClip is trained on Flickr images, so these are social media images. Mosaics is not a location encoder, but like a direct feature extractor from a satellite image database. And CSP is also a location encoder trained on iNaturalist imagery. Yeah, I even have this in here. So location encoders exist already, but none of them has really been trained with this idea of kind of broad geographic generalization and generalization across tasks in mind. Another thing that I unfortunately can't talk about too much because we did this internally at Microsoft, but I can give you a little bit of the intuition. It's kind of my favorite application of SACLIP is in building mass prediction. So often models that are trained on Western data fail when they're deployed in other countries around the world, in low-income countries especially. And building segmentation is a classic example for this. Here we have a satellite image of buildings in the US, where you can see that buildings are on the left side, where you see buildings are very rectangular, they're arranged in a grid, and they're kind of spaced out. On the right side, we have the same kind of resolution satellite image for Somalia, and still kind of a residential area, but you see that buildings are smaller, they're in all sorts of shapes, and they're kind of irregular arranged. And so a model that would be trained on US data might do pretty poorly at this data in Somalia. Now, the cool thing with SACLIP is that it has seen both of these areas, right? It hasn't learned to do building segmentation in both of these areas, but it has learned something about the unique characteristics of both of these areas. And it turns out that if we do a model transfer and add SACLIP into the mix, that this actually helps improve these modeling efforts. A similar idea is something that some other researchers have done. So this is from Nathan Jacobs' group at WashU. Here, people have used SACLIP to condition an image diffusion model for satellite imagery. So a diffusion model is a generative model for satellite images, and the authors here condition the model on an OpenStreetMap mask, so that kind of produces an image that has the same kind of buildings and streets as in the OpenStreetMap mask, and then they also condition it on SACLIP. And the best way you can kind of see the effect that SACLIP has here is that, keep in mind, SACLIP captures kind of very high-level features of a location, like climate zone, humidity, and so on. And if you compare images generated for example, Des Moines, Iowa, to Boulder, Colorado, you will see that the satellite images generated for Des Moines are much greener. And the reason for that is that Des Moines is much more humid, right? There's much more humidity, there's much more vegetation there. And this is exactly one of these big high-level features that SACLIP captures, and so it helps to kind of ground this model a bit geographically. All right, so this is kind of where we stand with SACLIP. This is kind of the experiments we've done. Where do we go from here with this kind of research? And what I really want to posit is that geographic encoders are a whole new class of geospatial foundation models that have global coverage and are designed for general purpose. They might not be the biggest models, right? The ones that we've trained so far are actually quite small, but they fulfill these kind of globality aspect of the foundation model. And I've kind of broadly outlined what I believe are going to be the main thrusts of research in this area in the next 6-ish years. 5-ish years. And I think the kind of first immediate impact of such models that we're already seeing today is that they are a great way for providing cheap and global location embeddings, especially in settings that are quite resource constrained, right? Not everyone can kind of afford to train a big computer vision model that takes in satellite imagery. Not everyone might have access to satellite imagery or be able to store it. Instead, you can just download our SACLIP model, which is a few hundred megabytes. If you remove the image encoder and just take the location encoder, it's even smaller. And then you can, for any location on the world, you can just query the corresponding location embedding and replace your image. For some tasks, that might be enough. For some tasks, it might not be. And in fact, we're seeing already quite a few kind of new papers on this. I think a bunch of the kind of big tech companies have caught up on this. I think the latest institution to release one is DeepMind. They have one that is more based on socioeconomic data and census data, but also really cool research. In the medium term, also in the short term, I think the next steps for expanding these models are also very clear. So far, we only use Sentinel-2 imagery, which is optical satellite imagery. There's many, many more remote sensing data sources we can adapt, like radar, like derived products, like vegetation indices. We can also work with data at different spatial resolutions and, of course, integrate the time component. Right now, SACLIP only takes in latitude, longitude. We do sample data from 2.5 years, I think. So we basically implicitly average over time or marginalize over the time component. We still represent all seasonalities, but having that time be like a free-floating parameter that you can manipulate yourself would obviously be really cool. Now, in the medium term, I think location encoders can be very useful for augmenting some sort of geospatial intelligence in LLMs. I haven't looked this up super recently, but the last time I did, it kind of still held true, and that is that kind of LLMs are not excellent at kind of geographic question answering. So here I kind of just dropped a pin in the Pacific and asked, this is GPT-4, to get me the annual mean temperature of the closest location that it has access to. And this location is somewhat close to Hawaii, so I would expect it to give me the annual mean temperature for Hawaii, but it kind of gets that distance calculation completely wrong and instead drops me somewhere in the Philippines. And so hopefully these kind of models, location embeddings, might again be able to condition bigger foundation models geographically and help with answering questions like this. I think generally this kind of alignment of embeddings from different modalities is super interesting here because it can really help with this translation between modalities, so from image to location to text to video. And I think we already see kind of first cool examples of this. So this is from a Python package, segment geo, that or SamGeo, that basically already integrates some sort of LLM component in like a GIS tool. You can basically type in a prompt like tree, and the model will kind of translate that into vision embedding space and then segment all of the trees in that image for you. It's like more like a gimmick at this point, but I think we're going to see a lot more of this in the future. Now, looking kind of further ahead, I think we are eventually arriving at a very big question, and that is, can we learn physical, environmental, and even social processes of our planet from data alone using neural networks? And can this help us identify and track changes in our planet? Might this even help with scientific discovery and extrapolation, right? If we learn like a good latent space representation of our planet that is dynamic from historical data, can we play these effects forward and analyze trends such as climate change? The answer to this, I think, is very unclear, but I think these kind of intermediate steps on the way are very useful in and of themselves. And I myself am very curious about these questions. I'm actually more optimistic than I was maybe a year ago. We're seeing great progress, not necessarily in remote sensing, but in other kind of adjacent areas of Earth systems modeling, especially in climate and weather modeling. I think we're seeing neural networks actually being really, really good. That makes me also more optimistic for this line of work. And yeah, maybe to end the talk, I'd like to direct you to our ICML position paper on this whole topic, where especially Esther Rolf, who's the first author on this paper, and us, we argue that we believe that it's kind of time for people to treat Earth observation and remote sensing data as it's a distinct kind of application area within machine learning, rather than having it like, you know, at a workshop here and there. But I think really it is unique enough and it is potentially impactful enough to have its own kind of, sub area, just like we treat biomedical imagery or so. And yeah, with that, these are the two papers I talked about today. Thank you to my amazing co-authors who've worked with me on this. Thanks everyone for coming and for your interest in this topic, and I'm excited to hear questions.